Okay, thanks a lot. So hello, and good afternoon from my side as well. First of all, I want to mention that we're both no sports scientists. We more come from the metrological side. So please excuse me if I don't get all the physiological terms right, but I hope that I can really show you with this presentation that a deeper knowledge for sensors and complex systems can also be very beneficial for the field of climbing research. So I want to start the presentation with an outline of what you can expect from my talk. First of all, I'm going to introduce our institute as well as the persons involved in this project. Then I'm going to talk about our motivation and why we think a climate performance assessment device is necessary. Next up, I'm going to present you our idea for a standardized, affordable, and easy-to-use sensor system. Then I'm going to show you our realization of a dual-arm climbing dynamometer, and I can also show you some first measurement results. And in the end, I'm going to talk about our next steps and what are our future plans and goals. So first of all, who are we? My name is Manuel Tanzer. I'm a PhD student at the Institute for Electrical Measurement and Sensor Systems. And together with me here today is Alexander Bergmann, who is the head of the Institute. Our institute is part of the Faculty for Electrical and Information Engineering, which is one of 7 faculties of the TU Graz. Right at the moment in our institute, we have 45 employees, out of which 40 are scientific staff, and we are located at the TU campus in Graz. Our institute consists of 3 major research groups. One of them is Sensor Systems and Sensor Physics, and is led by Alexander Bergmann. The second one is Energy-Aware Measurement Systems, and is led by Hans Wegleitner. And the third one is Photonic Sensors, and is led by Benjamin Lang. So what is our motivation? As we are both passionate climbers, we are talking a lot about in the past about is there a climbing performance determining parameter, and can you measure that? And we thought about bringing our knowledge about measurement systems, sensors, and complex systems in general to the field of climbing research. So why do we think we need a standardized assessment device? A very obvious reason is the sport's popularity is continuously growing. Either if you go to a track or in the local gym, more and more people are climbing, and more people are climbing at really high levels. And last year, climbing even got Olympic. In parallel to that, you can observe an increasing trend towards self-monitoring in everyday life. So nobody can imagine anymore going running without tracking his pulse, or in other sports, things like spirometry or tracking and analyzing an athlete's movement are already completely common. So why didn't it find its way to climbing yet? And an obvious reason, climbing is a highly complex sport. There isn't one parameter that defines an athlete's performance, but it's always an interaction of manifold different performance determining parameters. The graphic on the right side should just serve as a guidance to the eye and has no claim to be complete whatsoever, but I just want to show that some of the parameters are measurable, which are located more on the right side, and others like tactics, learning, pacing, and technique are very hard or even unmeasurable. Therefore, I think we should concentrate on the ones that we can measure reliable, and there we find that we have a lack of specific, objective, and affordable metrological devices. And from these devices, scientists, trainers, also the field of physical rehabilitation, and also protocols like LEA and PISTE, which evaluate the development of an athlete or its talent, could benefit from such devices. So what is our idea? First of all, we want to build a fully integrated and standalone sensor system. It should measure both arms simultaneously. And this is on the one hand to assess muscular disbalances, and on the other hand to create a more realistic measurement scenario. Additionally to the force sensing, we also want to synchronize our measurements with biometric data like SpO2 and ECG, for example, but we're not limited to that. One very important thing for us is the whole system should be standardized, meaning standardized Kanban runs, testing protocols, and training protocols, so that you can really periodically assess an athlete's performance and compare them over time. The system should be easy in handling. We want to create an app so that really everybody without pre-knowledge can use it, and it should have an integrated data evaluation as well as a progress tracker. The system should be affordable. There's no need for devices that cost a couple of €1,000. because then they're not open to anyone, and we really want that every climbing gym trainer or even ambitious amateur athletes can afford and benefit from such a device. And in the end, with our data, we want to create an open measurement database that scientists, trainers, and also private people can use it. We want to work on the basis of open science and create a universal data format so that, yeah, really everyone can create classifications, evaluate the data, and use it for its own cost. And now I can present to you our realization of the dual-arm climate dynamometer. On the graphic on the left-hand side, you can see our setup, which is quite compact. It can easily be mounted on any vertical space available, but we're also working on a standalone mounting system. You can see the two handguard rungs mounted individually, so you can measure both arms simultaneously. All it needs is basically a power supply, a standard 12 volts, and there's a reset button for the Bluetooth as well. A few words about the hardware. We have a custom-made sensor box as well as testing runs. Right at the moment, we have 10, 20, and 45 millimeters, but they can easily be exchanged to any other size necessary. We mounted the handguard rungs on telescopic slide rails to minimize friction losses. And as force transducers, we're using two S-shaped load cells. The data acquisition is then done microcontroller based, and the data can be transmitted via Bluetooth or via USB to the laptop. Until we have an app, I created a graphical user interface. It's quite basic. You can just start and stop a measurement, do some preliminary data evaluation, load open old data, and of course save some of your measurements. And quickly some specifications of our system. So the maximum data rate we can achieve is 80 Hertz, which I think is quite sufficient for this application. The dynamic range on each side is between 0 and 980.6 Newton, so 100 kilo, and the accuracy is plus minus 0.18 Newton. And as I said before, the grip types at the moment are 10, 20, and 45 millimeters. I really hope this works. I prepared a little video so they can see our system in action. Therefore, we mounted it in our local climbing gym, and I could motivate Peter Palmer, who is also participant of the FISU climbing championship later on, to test our system. Therefore, we let him try some of our preliminary testing protocols like maximum force pull-ups and repeaters. And yeah, as you can imagine, his results were quite impressive. And I think he also had fun, and he was quite enthusiastic about the whole system. Okay, is it okay? So next up, I would like to show you some of our measurement data, or how the data could look like. As we are no sports scientists, I don't want to give you any interpretation of the data, but I would like to leave it open to the experts. But we just had some preliminary testing protocols, like, for example, repeaters. We've seen them in some of the previous talks already. So the athlete had to hang for 7 seconds, 3 seconds off. We added as much weight necessary so that the athlete can't lift off the ground anymore. And the test was performed until exhaustion. And then you can easily do some mathematical evaluation of the data and determine things like critical force or whatever. Another protocol we used was maximum pull force. So the athlete had to perform 5 repetitions of maximum explosive pull-ups without any weight added. And therefore, you can easily read out the maximum force you can generate. And in case anybody wonders, the data shown here is not from Georg. His results were well above that. And the last protocol I would like to show you is a maximum force over time. So we again added weight so that the athlete can't lift off the ground anymore, and he had to hang there until failure. And here you can see a nice linear correlation between force over time. And finally, I want to come to our next steps and our plans and goals. First of all, right now we are working on additional sensor implementation. We have some biometric sensors for SpO2 and ECG available. This is done in cooperation with AMS Osram AG, and we're trying to bring them on the same platform to synchronize force measurements with the biometric data. Next up, we're working on an app development. As I said before, it should be easy in handling. Everybody should use it, should be able to use it without pre-knowledge. You will be able to create personal accounts and also track your progress over time. And then I come to a point which is very, very important, I think, is that you have standardized testing protocols which don't change over time. And therefore, we're looking for cooperations. So in case you think this tool can be beneficial for your research, please feel free to contact us. We are very welcome, or we would be very happy if you have some ideas for us. And in the end, again, we're going to create an open measurement database, and we hope that in the future we can maybe find some parameters, some measurable parameters, which really define peak climbing performances. And yeah, with that, I come to the end of my talk, and thank you very much for your attention.
Are there any questions for Manuel?
Sorry, excuse me, are you using for your hangboard standard 50 kilo sensors, like 4 sensors on the bottom? So, no?
2 load cells, each with dynamic range from 0 to 100 kilograms.
From 0 to, okay, thank you.
Yeah. Was another question?
Yeah, just my question. What is the use of it? Or why the ECG and SpO2? I wouldn't expect them to be hypoxic at any given time. So SpO2, what's the use for that, and why? Also, have you ever tried measuring ECG while someone's doing this? It's very, very difficult.
We haven't yet, but as I said, we're not sports scientists. But I think the SpO2 could definitely be very beneficial, as we've seen before, measuring blood oxygenation.
That's different. That's different. So SpO2 is what you're thinking of, is the oxygen bound to the arteriolar. This is different from SMO2, which is muscle oxygenation. It's completely. So there are different parameters. One is about basically your body being hypoxic, which is your SpO2, which you will not change in this because you're breathing. Unless you go train.
I found some literature on that, actually. I think Dave McLeod's used it for some of his papers.
They do that wrong.
Okay, then maybe come to him as a sports scientist.
Yeah. SpO2 is unless they need SMO2, muscle oxygenation, even infrared spectroscopy. SpO2 is via plasmography. It's different.
Okay. Yeah, that's very interesting.
It'd be interesting.
That's why I'm here.
Yeah.
We're looking for cooperation because, as you see, we're not expert in that field. But I think if anybody has some use for that tool and can bring us some input, we would be definitely glad to help.
I would say those 2 things are very, very difficult to measure with dynamically exercising. And the SpO2, I don't think we're doing.
Okay.
I'm happy to talk about it.
Thank you.